Let's talk about work and kinetic energy today. Yesterday we talked about power. Today we're going to talk about kinetic energy. I'm going to derive another formula for you. It's relatively simple. You are probably already familiar with that when work is done on an object, it may give it kinetic energy. If you push an object, it could speed up or slow down. It could give it kinetic energy. It could take away kinetic energy, I suppose. In general, we know that work done is equal to FD. Can you guys do that later, please? I was trying to get you to do it yesterday, but how about we do this, because this is important too. So in general, work done is equal to F times D. The energy transferred is equal to the kinetic energy gained by the object. So you might even say that the work done is equal to the kinetic energy if it had nothing to begin with. We're going to say delta EK, change in kinetic energy. I like to call it delta KE, kinetic energy, KE. EK is fine too, energy, kinetic, either one's good. But it's changing. Okay, so you're probably wishing you had a formula for kinetic energy. Hoping. Oh, we don't need that. I think that was back in the days when sound effects were cool. Since W equals FD and F equals MA, what'd you say, Lucky?
W equals mad.
W equals mad. Isn't that an awesome formula? W equals mad. Mass times acceleration times distance. But hold on, there's more.
So mass times acceleration times distance.
Not really one that we use a whole lot. You may remember from way back when, our old friend VF squared equals VI squared plus 2AD.
Yeah.
This AD right here and this AD right here seem to have looked familiar. If the object is initially at rest, then what happens?
VI is 0.
VI is 0, right? So if VI is 0, then AD is simply equal to VF squared over 2, right? And now this value here can go in there, right?
So that it's
Substitute this for AD, and we get EK is equal to mv squared over 2. The kinetic energy of an object is equal to its mass times the velocity squared divided by 2. Using this formula in my head, I was able to calculate just how fast someone was going at that ride at Canada's Wonderland that time. I estimated the height, estimated potential energy, converted it to kinetic energy, and
then
solved for V squared.
And then you got back to your hotel and you went and checked your word.
And I was close, and my family called me a nerd.
Estimate kinetic energy.
I estimated how high up the people were, right? That's a measure of gravitational energy, which is what we're going to look at tomorrow, MGH or MGD that we've talked about, right? So I estimated the height. I found an average, what's an average size mass for someone, right? Gravity, 9.8, I took 10, so it's 10 times the height, that's equal to U. Set that equal to this, in fact, the masses cancel out, right? So I took gravity times height, multiplied by 2, and took the square root to get velocity in meters per second. That's actually pretty simple. I didn't try telling anyone in line how it worked.
You've already experienced the ride in your mind, you don't need to do it.
What do you need to know? You need to know that EK is equal to mv squared over 2. That's it. But that's only true if an object starts at rest. Right? Only true if the object starts at rest. The work done is the total kinetic energy of the object.
So what happens to this?
Okay, so if the object starts at rest, the work done is the total EK of the object. What if it doesn't start at rest? If it's already moving, the work done is the change in kinetic energy, right? So the work done is equal to delta EK or W equals EKF minus EKI. Well, EKF, final kinetic energy, EKI, initial kinetic energy. What are you doing, Marshall? Let's go straight to sample problem, shall we?
No.
Let's jump right to the sample questions here. So a force of 25 newtons acts for a distance of 16 meters upon a 2 kilogram object which was initially at rest. Assuming no friction, find its final velocity. So what do I have here? I have force. I have a distance of 16. And I have a mass of 2. We are to find its final velocity. Well, let's calculate the work. 25 times 16, I think, is 400. Not meters, 400 joules. I got work equals 400 joules. The work is equal to the delta EK, kinetic energy. 400 is equal to...
Joules and impulse are both J.
J is a symbol in impulse. J is a unit when it's the end. Okay, so I set it into there. 400 is equal to my mass, 2v squared over 2. Conveniently, I put 2 in there. So V is the square root of 400, or...
Yeah, I'm confused with EK is now.
EK is kinetic energy. Okay, the work done is the change in kinetic energy. Because it was initially at rest, right? The change is equal to the final. Not that.
Oh, so the work, the change is also just the normal.
Well, anytime the initial is 0, the change is equal to the quantity, right?
I feel like you included the wrong answers.
Really?
Because number 1 here has fat ass.
Well, I think the questions also say there's some momentum in there, right? So, because it's kind of related a little bit. So, it's a nice little review.
Number 1 doesn't.
No?
Number 1, like we're doing right now.
No, this example one doesn't. He's talking about the problem. Let's have a quick peek at number 2. A force of 8 newtons acts for a distance of 5 meters upon a 4 kilogram body, which was initially already traveling at 4 meters per second. Find EKI, work done, final EK, final velocity. EKI, initial kinetic energy, is equal to mv squared over 2. So we're talking 4 kilograms traveling at 4 meters per second squared. Sorry, 4 meters per second, squared it, and dividing by 2.
That formula, the mv squared over 2,
Yep.
that's for the initial?
It's for kinetic energy. Could be initial or final, depending on whether your velocity is initial or final. Right? So I got 4 squared is 16 times 4 divided by 2 gives you, it has 32 joules of potential energy to begin with. Sorry, of kinetic energy to begin with. 32 joules of kinetic energy to begin with. How much work is done? Work is force times distance, 8 newtons, 5 meters, 40 joules. The object has 32 joules of kinetic energy to begin with, and I produce 40 joules of work. Where does that 40 joules go? It goes into increasing the kinetic energy. The work is the change in kinetic energy, or final minus initial. The work done is 40. We're solving for final. Subtract 32, goes to the other side, becomes positive. EKF is?
Is that 40? Or is that the atom or something?
This minus 72 goes to the other side and becomes plus 42, right? Stop and think about it. If you got 32 joules of kinetic energy, and you add 40, you got 72. The energy must be conserved. It has to go somewhere.
Yay for joules.
Yay for conservation of energy.
Are you doing conservation energy? No, how about conservation?
Conservation energy, what?
Conservation energy.
No. We got no time. Yeah, we're. Not happening.
Let's just make pancakes after the exam. How does that
You want to come in and make pancakes? We can have a group pancake breakfast. That sounds fun. D, final velocity. Eh?
Is it easy on me?
You want-
Easy, then I don't want to, but if it's actually challenging.
No, EKF's pretty easy, right? It's just equal to? Oh, D, yeah. 1/2 mv squared. How much, not delta EKF, how much kinetic energy does it have at the end? 72. EK equals 1/2 mv squared. The F is just if this velocity is F, right?
Yeah, but where did the half
Oh, sorry, my mistake.
So, okay.
For whatever reason, I've learned both ways, mv squared over 2 and 1/2 mv squared. And sometimes I just, yeah, they're both the same thing. Sometimes I just do want to think about it. Same thing though, right? Yeah, that's okay. It would look different, it's no big deal. Yeah. So V is going to be the square root of 2 times 72 divided by 4. Equals 6. Let's have a look at 3. Do
I don't have my stuff to look back. So
you want me to keep going, or you want to keep trying?
I want to do number 3.
Okay.
Wait.
Okay. 2 kilogram mass initially moving at 20 meters per second slides 150 meters on a rough surface where it experiences a force of friction of minus 2 newtons. Find EKI. EKI is equal to mv squared over 2. 2 kilograms, velocity 20 squared over 2 conveniently. Initial kinetic energy, 400 joules, right? Work done is F times D. It's friction providing the work, minus 2 times 150, or minus 300 joules of work. The minus just means opposite direction. But does it slow the object down?
Yes.
Yes, it removes kinetic energy. Where does that energy go? Heat.
You should have known this, though. You should know the final velocity of the
Pretty much.
quarter of force means half velocity.
Okay. Work is equal to EKF minus EKI minus 3. Is it important that the minus stays there? Does it mean something in this question?
Yes.
Absolutely, right?
Uh-huh.
The EKF is what we're solving for. The EKI was 400. So we add 400 to both sides. Final kinetic energy, 100 joules.
What number is that again?
That's the weird thing about physics is everything, like with the subscripts, you actually say it exactly backwards with the subscript.
I know.
Final kinetic energy is EKF.
EKF. It's like Pig Latin.
The weight force.
Yeah.
Yeah. It's just
It's just one of those rules of nature. Final here is going to be 100. Oh, there I wrote it the wrong way again for you, didn't I?
What is the formula you keep writing? Can you write that down? I want to see it.
I just wrote 1/2 mv squared, that's all. Same as mv squared over 2,
Oh,
right?
yeah.
just rather multiply
Yeah.
by 2.
I'll give you a couple minutes to try 4.
His face.
Through what distance must the 5 Newton force have acted in order to change the velocity of 4 kilogram mass from 10 to 15? So it's initially at 10 meters per second. It increases by 15 meters per second because some magical force, 5 Newton force, is pushing it. But the question is, oh, not 5. The question is, what is our distance? The question is, what is the distance? Okay, so let's start by finding EKI, and the formula, Mike, is mv squared over 2 for kinetic energy. Our mass is 4, our velocity is 10. 4 divided by 2 is 2, 10 squared is 100, giving me 200 joules of kinetic energy to begin with, right? Do I know the final kinetic energy? Well, I can solve for that. Okay, Sean, he just walked in, he needs to watch this.
I was giving him the formulas.
Oh.
So he knows.
Sorry.
Sean. Who knows what's going on?
The mass is 4, the velocity is now 15. Nothing's changed except I've put in a different velocity. I have 450 joules of kinetic energy at the end. My kinetic energy has increased. How come?
Because physics.
Because I did work. I applied a force through a distance. I did work. But I want to know how much distance, therefore I need to know how much work. Can you tell me how much work? Yes. Work is equal to change in kinetic energy. Yes, you wouldn't have got that yet, Mike. So we're talking about EKF minus EKI. The final was 450. The initial was 200. I did 250 joules of work. Very good. Work equals FD, 250 joules of work. My force was 5, giving me a D of 250 divided by 5, or 50 meters. I had to push for 50 meters to increase the speed. I'm going to very quickly tomorrow give you a brief idea about potential. Have you ever seen this abbreviation for energy, by the way? Yeah. Mr. Friesen used to use it, right? Okay, NRG. I'm going to tell you about MGH, which is equivalent to MGD, right? You kind of know this already, so it's pretty straightforward. And I'll make sure that I usually go a little bit further and talk about how potential energy and kinetic energy change to each other. I'll just give you the very brief basics tomorrow. That's Wednesday, right? Thursday will be review. Friday is the exam.
Where is it?
That's a